Welcome and settle in. Imagine yourself watching a small dust-lit room grow quieter as the evening breathes out, while somewhere above you the sky carries tiny travelers that drift without hurry, shaping the day's light and the night's calm. These are aerosols, little specks that hang in the air like soft punctuation in a sentence the planet has been writing for ages. Let your shoulders rest, let your breath find an easy rhythm, and allow the thought of these small particles to guide you into a slower pace. If you find comfort in these gentle explorations, please like this video and subscribe so you can drift off with us again, and feel free to start the playlist linked in the description to keep the soft learning flowing in the background. What city country are you watching from right now? Now, with your mind resting, imagine a single particle adrift in the quiet of the evening air. It is too small to see, even when a sunbeam touches floating motes in your room. It might be a fragment of sea salt lifted from a breaking wave, or a grain of dust carried across distant sand, or a delicate droplet formed from vapors that met and found a new way to hold together. It could be soot from a small flame, or a wisp of organic material released by a forest that sighs resin and floral breath into the atmosphere. Imagine it suspended, gently meeting the subtle jiggle of molecules, the soft jostle called Brownian motion, so gentle you could almost hear the hush of it if silence were a sound. Aerosols live between worlds. They are not clouds, yet they might become the seeds of clouds. They are not gases, yet they float with the same freedom. Some are solid, like tiny quartz shards borrowed from deserts. Some are liquid, like droplets of sulfuric acid or organics that cling together in microscopic spheres. Some are mixtures, shells and cores arranged like nested dolls, with a heart of soot and a shroud of clear material that gently refracts light. In that refracting and scattering, a delicate conversation with sunlight begins. You see it when the day is milky, when distant hills seem slightly veiled, when the sunrise becomes a soft painting stretched along the horizon. If you picture the planet as a quiet room, aerosols would be the dust motes that turn a plain beam of light into a visible path, making the invisible tangible. The room is vast. The beam is the sun, and across oceans and forests and cities, tiny particles steer the brightness and color, and they shape the ways clouds appear and fade. Somewhere far from you, in the high atmosphere above a tropical ocean, streaks of cloud form in lines that follow where ships have passed, their exhaust releasing particles that encourage more numerous but smaller droplets, brightening the clouds and making them linger. Imagine the open water below, a deep blue blanket, and above it a white gauze that forms and reforms, always slow, always soft. This is the to-me effect, described in simple rhythm. More seeds, more droplets, brighter clouds. It is not a drumbeat, more like the hush of waves meeting shore. Aero means air, and sol means solution. Aerosols often carry little dissolvable paths in them, and when moist air envelops them, water begins to gather. Picture a particle and a whisper of humidity, and then a little curve of physics called the Kohler curve climbing and descending as the particle encourages a droplet to grow. The particle's saltiness, or its organic nature, matters. Some are generous to water, and welcome it eagerly. Some resist. As humidity rises, the droplet grows more than you might expect, swelling from a speck to a pearl of cloud water. You find yourself imagining this growth as a gentle swell in a slow tide, not urgent, but persistent. Not all aerosols cool the air they travel through, though many do. Most scatter sunlight back to space or sideways into shadow, making the ground a touch dimmer and the color of the sky softly diffused. Sea salt and sulfate often scatter. Dust can do both, depending on its mineral heart. Soot, known as black carbon, absorbs. When you think of black carbon, minimize the harshness. It is simply a flame's memory, a carbon skeleton that drinks in light and warms the air around it. Warmth in the air can thin clouds, can give them a different posture. This is sometimes called the semi-direct effect, a tender change in posture rather than a sharp switch. The changes happen in whispers over hours and days, not in sudden clatter. Imagine now a long journey. A desert breathes, wind battles at the surface and lifts a fine powder aloft. The dust rises and settles into the trade winds, begins a languid voyage westward, crossing an ocean without a map, day after day, like a low murmur across water. The Saharan air layer keeps it aloft, warm and dry, so it travels farther, and on that journey, it dulls the sunlight just slightly, and it brings nutrients tucked into each grain. When those grains fall into the sea, they carry iron, a tiny feast for plankton that set off delicate blooms, green stirring in a blue expanse. And when those grains land in a rainforest across the ocean, they bring phosphorus, a slow gift from one continent to another. The gentle rhythm continues, the planet trading materials without hurry, a quiet sharing arranged by the wind. At the ocean's surface, whitecaps break. Each burst scatters droplets into the air. The water inside evaporates, leaving sea salt crystals wrapped in tiny films. These crystals are welcoming hosts to water, and when moist air embraces them, they swell so readily that cloud droplets gather wherever they drift under a sky cooled by night. In summer, forests release terpenes that smell of pine and citrus. Those invisible scents meet oxidants in the air and form new particles, delicate clusters of organic molecules that join the haze. In places like the southern Appalachians, the haze gently blue shifts distant ridges, so they look soft and layered, like watercolor paintings blending at the horizon. The gentle rhythm continues, a slow exhale from land and sea that makes the air's fabric more intricate. Aerosols do not live as long as the gases you may hear about in discussions of warming. Greenhouse gases linger for years, decades, centuries. Aerosols typically drift for days to a couple of weeks. They are short stories in a library of long novels. However, their stories come in huge numbers, and their constant renewal means they are always riding across the sky, shaping reflectivity, sculpting cloud cover, influencing rainfall patterns, and nudging temperatures in delicate ways. Because they are short-lived, their patterns are uneven. One region may feel their cooling touch more than another. One season may bring more scattering haze or more absorbing soot than the next. The gentle rhythm continues with a slightly different tempo in each place. The life of an aerosol involves gatherings and farewells. Particles meet each other in the air and sometimes join, merging into larger bodies in a process that feels, conceptually, like two raindrops on a window gliding into one. This is coagulation, but you can think of it as small things finding each other and becoming less numerous, but larger. The air clears slowly as particles shall coalesce. Then it fills again when new ones form from gases that meet and condense. In the end, most aerosols leave in rain. Clouds sweep them up, droplets collide and grow, and the particles are hosted in raindrops that fall to the ground. The quiet drumming you might hear on a roof during a calm rain is a kind of release for the air, a cleansing that restores clarity behind the storm. Dry deposition happens too, invisibly. Particles settle under gravity or brush against leaves or meet the cool surfaces of buildings and ground when the night air brings them nearer to the earth. Dew can gather them, and morning light will lift some again. Volcanoes tell a different story. When a volcano breathes into the stratosphere, sulfate aerosols form high above the everyday weather. They form a thin veil that circles the globe, a diaphanous scarf of droplets that scatter sunlight and cool the surface below for a little while. The sunsets become more vivid, colors stretching longer, and the planet breathes a slightly different tune. This is not dramatic, but it is noticeable if you know to look. You might imagine the world with a quieter sun for a year or two, a gentle dimming, and then a slow return to normal as the droplets fall away or are carried to other layers of the atmosphere. The gentle rhythm continues, an atmosphere that remembers each event with a subtle note. You may be thinking of clouds again, because aerosols and clouds are deeply intertwined. When many small particles are present, the same amount of water condenses onto a greater number of seeds. The cloud becomes made of many small droplets rather than fewer large ones. Small droplets fall more slowly. They collide less often and coalesce into rain less quickly. The cloud lingers, bright and consistent, and the sunlight it deflects is a soft quieting on the surface below. Imagine marine stratocumulus over a cool ocean current, a wide sheet of white stretching out for hundreds of kilometers, its texture gentle, its underside a calm gray, its top a field of softly lit humps, like cotton pressed flat. Small changes in the number of cloud droplets can alter this sheet, opening pockets where drizzle forms or tightening the weave where drizzle is suppressed. In satellite images, shipping lanes sometimes appear as long, narrow mirrors in the sky, where exhaust particles have brightened the cloud line. Recently, as fuels have been cleaned and sulfur content reduced, those lines have grown fainter, a quiet adjustment in the fabric of clouds. The sky adapts, and the gentle rhythm continues. When you are indoors and a sunbeam crosses the room, the motes turning and gliding within it offer a small analog for what the planet experiences on a grand scale. But out there, every region has its signature blend. The Arctic in late winter and early spring holds a gentle haze transported from far away, a hush of industrial and natural particles that drift into the long twilight. Dust storms in the spring and early summer cross oceans, their plumes subtle at altitude but felt in a fine film on distant shores. Forest fire smoke in late summer builds vertical towers of cloud when the heat rising from flames becomes strong enough. These clouds can loft plumes into the upper layers of the atmosphere, where they wander for weeks. Over the Indian Ocean, a seasonal brown haze can gather and lean on the monsoon's edges, shifting where and when warm rains arrive. None of this needs to be dramatic to be powerful. It is a gradual rearrangement, a slow choreography, and the dancers are tiny. Aerosols affect not only light, but also heat that rises from the surface. At night, the Earth emits long-wave radiation, and certain particles can change how that radiation escapes, though their role is subtler than that of clouds or greenhouse gases. When aerosols alter clouds, the balancing of energy between day and night also changes. Over brightened regions, daytime cools gently. Over absorbing particles that warm the air, stability can shift, sometimes clearing clouds, sometimes thinning them. These changes shape where rain falls, the timing of showers, the strengths of storms, the quiet days when nothing much happens, or the weeks of low gray ceilings. All are influenced by the tiny and short-lived travelers. To understand them, people build instruments that listen to the air, on high hills and on flat coasts, on ships and on aircraft, and in a network of simple stations that watch the sky with patient eyes. Measurements accumulate. A line of light shines through a chamber to see how much is scattered by the particles inside. A black filter darkens as soot is drawn onto it, a controlled breath that reveals how much absorbing material the air carries. A lidar sends pulses upward and reads the echoes, a soft echolocation for haze layers. Satellites above look down and infer the thickness of the aerosol veil through a quantity called optical depth. Optical depth is a way to say how much the particles dim the view. High optical depth, the air looks gauzy. Low optical depth, the air looks clear. None of this is rushed. Instruments collect data day by day, and careful hands compare, calibrate, keep the records tidy so that slow truths can be seen. Aerosols are varied and come from many sources: spray from the sea, dust from land, sulfates from gases that oxidize, often from sulfur dioxide released by volcanoes or from human activities. Nitrates that grow on the bones of ammonia, drifting from fields and farms. Soot from diesel engines and cooking fires, and biomass burning constrained and reduced in many places, still important in others. Organic particles from trees and crops and cities, some of them absorbing in the blue like a faint tea stain in light, called brown carbon. Each type has traits that affect how it interacts with light and water. Sea salt loves water and becomes large easily in humid air, casting light generously and seeding clouds. Sulfate does much the same. Nitrate shares similar tendencies. Soot resists water unless it is coated, but it drinks light and warms modestly. Dust can carry iron and calcium and other minerals within it, giving the air a subtle chemistry lesson wherever the wind carries these tiny samples. At night, chemistry continues in the dark with a different cast of characters. Certain reactive molecules awaken in absence of sunlight. The air is a quiet laboratory with almost no sound. Gentle currents moving through spaces you will never see, performing transformations that prepare the next day's haze. In forests, the scent of pine and earth meets these reactants and softly becomes less volatile, condensing into particles that add to the morning's blue haze. Imagine walking through such a forest in the early hours with dew on leaves and a mild scent of resin, and then lift your mind toward the canopy and into the air, where these transformations drift and settle like a gossamer. Consider the path of a single aerosol from the surface to a cloud. Imagine yourself at the coastline, sitting on a low stone wall, the sea before you, a calm slate. A small wave rolls and breaks. A burst of spray rises and falls again. One droplet lingers in the air, water evaporating until a salt crystal remains. Tiny as a suggestion, a breeze lifts it. It wanders inland, slowly rising as the day warms. The air becomes humid, invisible vapor waiting for a place to rest. When the air reaches a slow-moving, rising current, perhaps along a gentle hill or over a sunlit field, water begins to gather on that seed and a cloud droplet forms. From below, the cloud appears like a soft white field being sown, each droplet a stitch, each stitch supported by a seed. That droplet moves with the cloud for a while. As more droplets form, the cloud brightens. Gravity is patient. The droplets fall so slowly that upward motion holds them near the same height, a kind of floating rest. In time, droplets meet and combine, and rain begins slow at first, a whisper on leaves, then a quiet pattern on your stone wall. The seed inside the drop returns to earth, maybe to the same ocean it left. The gentle rhythm continues. Aerosols pull invisible strings in climate. In the middle of the 20th century, as industries and cities grew and the air carried more sulfate and other cooling particles, the global surface felt a slight dimming. Temperatures rose more slowly despite greenhouse gases increasing. When air quality began to improve in many regions and emissions of some aerosol precursors decreased, the dimming lessened and the warming became more apparent. The story here is not a caution with sharp edges, but a reminder that the planet responds to what we release, and the response can be a layered combination of coolness and warmth, of cloud and clear days, of rain patterns shifting by modest amounts, and of regional differences that matter for gentle discussions of weather and seasons. The gentle rhythm continues, a long interplay of causes and effects. Over oceans, the type of aerosol matters greatly for cloud behavior. Marine stratocumulus thrives on clean air that supports cloud sheets extending over cool currents. Yet when extra particles arrive, they become brighter and less prone to drizzle. In certain places, this can increase the amount of reflection to space and cool the sea surface below a little. That coolness feeds back to the cloud layer by reducing turbulence and maintaining the inversion that supports the cloud like a soft brace holding a smooth ceiling in place. This interplay can create open and closed cells of cloud honeycomb patterns visible from above. Where drizzle breaks the pattern, open cells appear with darker areas and visible lines of precipitation. Where drizzle is suppressed, closed cells spread, a smoother sheet. If you picture this from space, imagine a quilt of white squares slowly rearranging itself. Farther inland, particles can shift the timing of afternoon showers by affecting how quickly clouds grow and rain forms. In mountain valleys, where breezes and upslope flows are part of the daily rhythm, aerosols can tilt the pattern a little earlier or later, a softer or sharper crescendo. In monsoon regions, aerosol layers influence the strength of the thermal contrast that drives winds from ocean to land and then back. Over the Indian subcontinent and the adjacent ocean, this complex dance involves moisture, temperature, and the murmur of a haze that absorbs and scatters in different amounts at different times of year. The result is a shift in the distribution of rainfall, sometimes more in some areas, sometimes less, and often a change in where the early season or late season showers become steady. When fires burn through forests or grasslands, the smoke that rises carries soot and organic aerosols. The sky takes on a pale tan or soft gray, the sun a muted disk that could be looked at briefly through thin layers without strain. In high latitudes, boreal forest fires can send smoke high into the atmosphere where it lingers, drifting for long distances. The burnt fragrance is not the message we dwell on here. Rather, it is the way smoke becomes a light filter and the way it can alter cloud properties by adding many small seeds. Over mountains, the combination of smoke and afternoon heating creates delicate cloud streaks with long shadows that paint valleys in quiet filters of shade. Over the ocean, smoke that rides far from shore may seed cloud decks that sparkle brighter on some days and then fade on others. The gentle rhythm continues, a diffusion of substances and effects, never in a hurry, always guided by wind and the structure of the air. In cold regions, where snow blankets the land and ice drifts on the sea, dark particles that settle on the white surface change the way sunlight is absorbed. Even a faint sprinkling of soot can make snow a little more eager to warm and melt. This is not dramatic in a single moment. It is a seasonal whisper. Over time, the timing of melt changes, which affects plants that wait under snow, and the timing of streams rising with meltwater. The streams murmur earlier or later. This is a circulation of cause and effect that extends from the highest atmosphere to the smallest rivulet on a forest floor. Consider for a moment the smell of the sea on a cool morning. Much of that scent is made by the ocean's living communities, tiny organisms that change chemicals in the water, releasing gases that the air lifts and transforms. One of these, often discussed with calm curiosity, forms sulfate particles after meeting oxidants in the air. In the southern oceans, far from continents, this biogenic pathway contributes to the haze that gently brightens clouds over cold waters. The ocean breathes, and aerosols join the sky as a result. The gentle rhythm continues, a pulse of interactions that aligns with waves and winds. The science that describes aerosols and climate thrives on models that simulate the atmosphere in delicate pieces. A model divides the world into tiny boxes in the sky and near the surface, with rules to move air from one to another, to condense vapor, to let particles form and grow and be washed out. Inside these models, aerosol cloud interactions are simplified in ways that are gentle approximations. For example, instead of tracking every particle, a model might keep track of a few kinds, each with representative behavior. The critical supersaturation needed for droplet activation is computed from parameters like hygroscopicity, say a single number that captures how welcoming a particle is to water. Many small droplets mean a greater total surface area for reflection, a brighter cloud, a longer-lived sheet. When the model's grid is coarse, the details of turbulence and cloud structure are blurred, so another model, smaller and more focused, is used to test the physics with higher resolution. People call these cloud resolving or large eddy simulations. Imagine a series of nested dolls of representation, each layer smoothing or elaborating the one within. Gentle conversions link them, like a translator telling the same story in simpler or more detailed language. Because there are many moving parts, there are uncertainties. The amount of cooling aerosols provide at the global scale, balancing some of the warming from long-lived gases, still carries a spread in estimates. Observations help narrow this range. Satellite tracks that catch ship lines and cloud decks offer real-world tests for the way cloud droplet numbers respond to particle numbers. Remote islands in the Southern Ocean provide windows onto pristine air where the natural baseline can be studied. Cities offer the other end, where emissions are varied and complex. Over time, as measurements accumulate, as instruments improve, as models learn from what is observed, the picture grows clearer. Not perfectly sharp, but clearer in a way that satisfies a patient curiosity. Policies that reduce emissions of aerosols, especially those that affect health at the surface, are successes where air becomes easier to breathe and the light through a window feels cleaner. These reductions often reveal more of the warming driven by greenhouse gases that remain in the air for longer. The path forward becomes a careful balance, reducing short-lived cooling particles while also reducing long-lived warming gases. So that the climate finds a softer landing, it is a reminder that almost everything in the air is connected to choices made with hands and machines and schedules, and to processes that existed long before humans, all weaving together in a single moving quilt. On an evening walk, the scent of wood smoke from a small controlled fire may drift through the air, and in a sunlit kitchen, dust may glitter as you wipe a shelf. These are small echoes of the larger atmospheric processes, yet the scale outside your window is enough to imagine the rest. Picture a dust plume crossing an ocean. Then picture a sea breeze pushing light salt crystals inland. Then picture a city's towers softly exhaling a million tiny soot particles that quickly meet other vapors and become different than when they left. Then picture a storm that rises and washes many of them out. Then picture a clear morning after, blue and crisp. All of it feels like breathing. Even a single moment in a day can be traced through the ebb and flow of aerosols. Around sunrise, the air near the surface cedes its night cool to the sun. A little stirring begins. Visibility improves as particles mix upward. If humidity is high, they swell and scatter light, so perhaps the horizon is soft. If the air dries with warming, they shrink and scatter less, and distant features become clearer. Around midday, the mixing is deeper, and particles are lofted high, the boundary layer like a basin being stirred. Late in the day, as the sun lowers, humidity rises a bit, and the haze returns. Then, the night settles. The mixing layer shrinks, and particles near the ground accumulate again until the first breath of dawn lifts them. The gentle rhythm continues, a daily cycle that plays a low melody. Sometimes the sky writes messages in invisible ink and reveals them only through instruments. One of these messages speaks of a property called single scattering albedo, a way of saying what fraction of light is scattered versus absorbed by a mixture of particles. In a quiet lab, a scientist adjusts an instrument that measures this value notes a small change and sees that a particular day's air is more absorbing than the day before. The shift could be the passage of a smoke layer or a different mix of urban emissions under a new weather pattern. Tiny variations like these are the threads from which a tapestry is woven. The tapestry is not loud, it is textured and pale with occasional darker swirls. The mind can rest within it. Another hidden message appears in how particles activate into cloud droplets. The number of particles that can do so at a given supersaturation is called the cloud condensation nuclei spectrum. It is a gentle curve like the outline of a low hill. At low supersaturation, only the most welcoming particles activate. At higher supersaturation, many more do. The interplay between turbulence, which briefly elevates supersaturation, and particle properties, which set the activation threshold, determines how many droplets a cloud will adopt. In places with strong updrafts, like summertime cumulus over land, a burst of activation creates many small droplets that sparkle as sunlight passes through the cloud's edge. In calmer marine layers, where updrafts are mild, particles must be truly hygroscopic to help the cloud. The gentle rhythm continues, a pattern of vapor meeting seeds that is as precise as it is slow. You might imagine being a traveler perched quietly on a ridge above a wide plain, watching a dust plume move toward you all afternoon. It looks distant and smooth from far away, a faint beige brushstroke against pale blue. Hours pass without urgency. When it reaches your ridge, it ushers in a mild dimming, the light warmer, shadows softer. The taste of the air becomes faintly mineral, the smell dry and old, like earth turned by a quiet hand. Then it passes, and in the next day or two, traces of it appear in puddles after a small rain, settling at the bottom in fine arcs that look like feathers when the sun returns. Elsewhere on the same planet, a fisherman prepares nets, while a low marine layer blankets the sea in a ceiling not high above the mast. The edges of the cloud are luminous where the sunlight hits, and underneath it, the world is the color of early morning. A ship passes, leaving a pale stripe in the cloud that no one on deck can see from below, but that satellites trace as a signature that reveals the presence and effect of aerosol particles. When the clouds later clear, the surface ocean is a shade cooler in that corridor, and the air above it responds with a slightly different breeze. The gentle rhythm continues, and ocean and sky conversing in lowered voices. At small scales, the physics of scattering is a modest delight to imagine. When a particle is much smaller than the wavelength of light, scattering is more efficient for shorter wavelengths, which can make the sky a calmer blue. As particles grow to sizes comparable to or larger than the wavelength, scattering becomes more complex and less color selective, and the glaze of haze becomes more neutral, like a veil of white. If the particle absorbs more like soot, it removes light while gradually warming its surroundings. A coated soot particle can act like a lens, with a brighter shell holding in a darker core, leading to tiny complexities in how much absorption occurs. All of these behaviors happen millions upon millions of times in any piece of the sky you look at, but the result is smooth. Nature adds many tiny quirks to yield a very simple look for human eyes. The gentle rhythm continues. Around the midpoint of our slow journey together, it can be nice to touch base with how you feel, to anchor this learning in the comfort of the moment. How sleepy are you on a scale of 1 to 10? Now, let us return to the flow of air. Over farms, the ground releases ammonia, a gas with a soft, acrid whisper, which later meets nitric acid in the air to form ammonium nitrate particles. These are often present in cooler, humid conditions and can be a significant part of haze in certain regions. Over cities, nitrogen oxides and sulfur dioxide are transformed by sunlight and oxidants, becoming nitrate and sulfate over time, joining with ammonia to form stable salts. Organic vapors from traffic and cooking and solvents react too, creating a complex cocktail that condenses when it can, filling some of the same roles as natural organics. At night, a reactive form of nitrogen, the nitrate radical, becomes more abundant, quietly pushing chemistry forward while we sleep. The next morning's air holds the results, which you can imagine as additional brushstrokes on a canvas, not obvious individually, but part of the whole scene. If you travel in your mind to a pine forest in northern latitudes, you might picture cool air, a peppery sweetness, and the slight blue haze that smooths distant trees. That haze is a reminder that biology does not end at the boundary between leaf and air. Trees release molecules during the day that can protect from heat or send signals or simply be byproducts of living. The atmosphere receives them and reshapes them into particles. In the Great Smoky Mountains, the name is a simple description of the look of the air on calm summer days. The same process occurs in many forests across the world, sometimes making a faintly sweet scent that explains why an alpine breeze can smell like citrus and honey and pine at once. The gentle rhythm continues, with life on land and the sky above trading pieces of themselves. Far above this, in the stratosphere, a different, thinner life for aerosols plays out. When a great volcano sends sulfur dioxide high into the sky, the chemistry there is slower, but it forms sulfate droplets that remain for months to a couple of years. They spread around the world along latitude bands like well-placed ribbons and cause a modest global cooling by reflecting sunlight. At sunrise and sunset, these layers can also scatter the sun's light in ways that make the colors richer and more prolonged. Painters have recorded sunsets during such times, and the sky reads differently in their work, a warmer glow for a longer stretch. The changes do not last. Gravity and slow circulation bring the particles down, and the stratosphere returns to its clearer state. The gentle rhythm continues. In snowy landscapes, a quiet consideration arises. When spring sunlight rises higher in the sky, snow that has been softened by dark specks melts a bit sooner. Instructions for when birds nest and when flowers push through the last crust of white can shift by days. It is a reminder that tiny particles, almost weightless, have the power to become part of the timing of life. None of this needs a dramatic telling. The idea itself is enough to hold and then set aside, letting your mind drift back to the present comfort. Picture one more journey. Start in a city with a scattering of sounds and lights, but imagine them muffled like a blanket placed gently over the hum. An evening breeze moves through streets and carries upward all the day's messages in the form of gases and aerosols. Some will be washed out by a shower, sweeping in from nearby hills. Some will be transported into the free troposphere as a storm's outflow lifts them high. Some will meet and merge. Some will shrink and vanish as gas again. Some will coat each other and change identity. Over a few days, the mix that once lingered near you becomes a diffuse background stretching over the countryside, and then declines as rain and settling remove it. The city's lights emerge clearer the next evening, and the cycle repeats. In many parts of the world, air has grown clearer in recent decades thanks to policies that reduce emissions of sulfur and soot. When fuels change and filters improve and cleaner energy steps forward, the atmosphere responds quietly. In shipping, reducing sulfur in fuels made certain ship tracks fade, a subtle change in cloud patterns that instruments noticed long before most people did. The open ocean sky now carries fewer of those lines. The gentle rhythm continues as the world's decisions write themselves into the weather and then into the climate. One day, a person folds up a portable instrument, steps out of a small research plane, and looks at the sunlight through a thin veil of smoke at high altitude. The instrument recorded how much light was scattered and absorbed as the plane traced a pattern across the plume. In the days to come, the person and colleagues will compare these readings with what satellites saw and with what ground sensors recorded hours later when the plume passed overhead, comparing the gentle peaks and valleys in the graphs to see if the models can follow the same rhythm. They will tweak parameters, adjust assumptions about how quickly particles age and develop coatings, and test how activation into cloud droplets is represented. The work is patient. Progress accumulates as a soft stack of papers and shared codes and long conversations. In another lab, someone studies brown carbon, those organic aerosols that absorb light more strongly in the short wavelengths, giving a slight warmth and tint to a smoke layer or to urban haze. This absorption can decrease as the particles age, especially when sunlight bleaches them over time. Imagine the absorption gently fading like a fabric left in the sun. The role of brown carbon in climate is still being quantified, and for now, you can simply imagine it as a faint tone in the spectrum of aerosols. The cryosphere speaks softly about aerosols too, in the high Himalaya, in the Rockies, in the Alps, and across the Arctic. Snowfall can capture the story of distant fires and cities, layering dark particles into the white. When snow melts, those particles sometimes remain atop the surface, making it slightly darker still until they are washed deeper or carried away by wind. Meltwater that travels into lakes and rivers carries traces of these particles far from their sources. A glacier may keep a record of past years in shallow bands of this kind of dusting, and climate scientists read these strata with a calm forensic patience, uncovering the timing of large fires, dust storms, and even volcanic eruptions, all gently preserved in ice. The question of purposeful aerosols, of whether humans might one day try to mimic the cooling after a large volcanic eruption by placing reflective particles into the stratosphere, is discussed in careful tones. The idea is to dim sunlight slightly to offset some warming. The risks include complex changes in rainfall and regional climates that we do not yet fully understand, and the idea comes with ethical and governance challenges that are as important as the physics. If this concept enters your thoughts as you drift toward sleep, let it rest there as a possibility under study, not a plan pressed forward, a reminder of how intricate the system is and how gentle we must be in any steps we might take. Back at the surface, consider the sound of rain on leaves and the way it clears the air in a valley. When a storm has moved through, the world sometimes looks etched more finely. Edges sharpen. The scent of soil becomes damp and comforting. This is because the rain has scavenged particles, wrapping them into droplets that fell and returned them to ground and water. Afterward, the air contains fewer seeds for clouds, fewer sites for scattering. The evening may be bright in a different way. If mist forms later, it grows from a cleaner set of seeds, and the droplets are perhaps a little larger and less numerous. The mood of the valley changes, a small response to a small reset, and by the next day, particles will have returned from new sources, starting the cycle, the gentle rhythm continuing. Aerosols and clouds also talk in the language of drizzle. In a marine cloud layer, drizzle drains water from the cloud more quickly and can thin or dissolve the cloud bank. Aerosols that increase droplet number can reduce drizzle, letting the cloud bank persist longer. The result is a change in cloud cover that extends for many kilometers. This is not a sharp edge, but a slow drift. The sky has a memory of aerosols in this way, remembering through the persistence of clouds and through the surface cooling that helps sustain the inversion. You can imagine the cloud deck as a wide, shallow lake of droplets floating above the sea, with aerosols acting like pebbles that alter the smoothness of the lake's surface. At times, aerosols hitch rides on strong currents that cross from one continent to another, and then to a third. Saharan dust to the Caribbean, ocean dust and pollution to the western coasts of North America, smoke from far northern fires over Europe, each following seasonal pathways set by the general circulation. The layers stack and mix. An airplane passenger glances out the window at a smooth gray band at the horizon and does not know that thousands of kilometers of travel have produced that single gentle line. Instruments on board a satellite overhead see more. They record the layer, its height, its thickness, the subtle difference between scattering and absorption, and they send the data back. The data set grows, and the next generation of models learns. Hygroscopic particles like sea salt do something else in humid conditions near the coast. They take up water and become large enough to fall more quickly, a small sink that makes coastal air sometimes clearer at midday when the humidity dips. Later, in the evening, as humidity rises again, these same particles swell and the world acquires a milky softness in the lights of a harbor. The gentle rhythm continues day to night to day, with the size of particles changing with humidity, modifying the way light slants and how far you can see. When people speak of aerosol optical depth, they summarize the column of air above a point and how many particles it contains that affect the path of light. During a dust event, the optical depth increases and the sun thins to an amber coin. After a rain, the optical depth decreases and the sun becomes crisp again. This measure is dimensionless, but it ties to the visible. to the way things look and feel. The word depth is apt, as if the air were a pond with variable transparency, and aerosols were fine silt suspended after a stirring wind. Another property, called the angstrom exponent, tells us about the relative size of the particles. Higher values often mean smaller particles. Lower values tend to mean larger, coarse particles, like dust or sea salt. On a summer day, instruments may report a higher angstrom exponent in cities where fine pollution is prevalent, and a lower one near beaches when surf is high. With just these two numbers, optical depth and angstrom exponent, experienced eyes can sketch a story of what kind of aerosols fill the air. The story is told without hurry, perhaps over tea, by someone who has spent many such afternoons watching the sky and noting its changes. Slowly, we return to the clouds, because they are the fabric that aerosols embroider. When a cloud's droplets are many and small, sunlight reflects in such a way that the cloud appears bright from above. As the cloud matures, autoconversion, the process by which droplets grow into drizzle drops, depends on droplet size distribution. Many small droplets take longer to coalesce. This delay can lengthen the cloud's life. For marine layers that already tend to reflect the sun's energy, this is a small but significant reinforcement. Over land, for convective clouds that rise like towers, the story is more complicated. Updrafts, entrainment of dry air, phase changes of water, and the presence of ice all share the stage. Aerosols alter the balance among these processes, sometimes deepening convection, sometimes suppressing it, sometimes shifting anvil coverage, and the spacing of storms. Each of these changes can lead to modest shifts in rainfall, in sunshine reaching the ground, and in the daily balance of heat. As you imagine these clouds, let your mind's eye soften focus. See the towering edges lit with late afternoon sun, and then see the edges blur as they mix with surrounding air. See the faint curtains of virga that never reach the ground, drifting from the base of mid-level clouds. Visualize the glows around the sun, called halos, when tiny ice crystals refract light in high cirrus. And remember that even there, the seeds of those crystals may have been particles lifted from continents far away or from the sea below. The air is full of potential forms of droplets and crystals, and aerosols set the table for these forms to appear. The gentle rhythm continues. When aerosols deposit onto the ocean, they become part of the ocean's nutrient cycles. Iron from dust can stimulate phytoplankton growth in certain iron-limited waters. Phosphorus and other micronutrients can nudge ecosystems. In turn, the plankton can release gases that form new particles, closing a loop that begins and ends with the sea. This is a planet-wide conversation carried by air and water, slow and understated. When you look at a map of ocean color from a satellite, a greenish bloom appears where dust has recently fallen. The edges soft, the shape a smooth flourish that fades in days to weeks. The bloom changes how much sunlight the ocean absorbs, how much carbon dioxide is taken up, and how the atmosphere's humidity interacts with the boundary layer. The gentle rhythm continues inside the sea as on its surface. In landscapes of grass and open land, dry season winds sometimes carry fine ash and dust from fires and bare soil. The air appears golden in the late afternoon. Later, when rains return, the air clears and the ground holds on to the particles that were once skybound. You can imagine a raindrop striking soil and embedding a tiny soot particle that once floated above a distant ridge. You can imagine the same particle being taken up by a seedling, but we need not follow it further, only appreciate the cycles that move matter and energy in such quiet ways. The path ahead for aerosols includes continued change as energy systems evolve and land use shifts. In many regions, emissions of sulfur have fallen and will likely continue to fall, which reduces sulfate aerosol and the associated cooling. Emissions of organic aerosols and black carbon from fires may respond to climate and to management of landscapes. Agricultural practices influence ammonia release and thus nitrate particles. The patterns of natural aerosols like sea salt and dust respond to winds and waves and to the dryness or wetness of soil surfaces. It is not a puzzle with a single solution, but a living mosaic. Models incorporate expected changes in emissions and climate and offer projections, and the differences among them measure our uncertainty. As the years unfold, observations will keep watch and provide quiet corrections, so the models move gently closer to reality. At a human scale, the experience of aerosols is immediate. The clarity of a view from a hilltop, the softness of a sunset, the way stars look brighter after a rain, the faint smell of the ocean carried inland, the silent midday haze that makes a mountain look not far away, but dreamlike. In each of these experiences, you are part of a climate conversation that is both vast and subtle. When you close your eyes at night, the air around you still holds its mixture, and even though walls define your room, the connection to the outside continues as slowly changing indoor aerosols settle on surfaces or are gently drawn through filters. The same physics applies in miniature, the same easy settling under gravity, the same soft scattering of light in a sunbeam. The gentle rhythm continues in your home as it does in the world. Perhaps, with eyes almost closed, you imagine a planet seen from far away. You would notice the white curtains of cloud, the tan strokes of desert, the green and dark blues of forests and ocean. You would not see the aerosol veil directly, but you would see its effects in the brightness of certain cloud decks, in the pale blue edges where dust rings color from the sky, in the long shadows at twilight after a distant volcano breathes into the stratosphere. If you watched for weeks, you would notice patterns, seasons turning, storm tracks curving, monsoons arriving and retreating, hazes gathering and dispersing. The longer you watched, the clearer it would be that the small shapes the large, that the tiny particles steer bigger climates, not with a shout, but with endlessly repeated whispers. And under this view is the physics, steady and accurate in its essentials. Tiny particles scatter light according to their size and composition. They activate into cloud droplets or into ice crystals, depending on their nature and the environment. They are born and transformed and removed along many roads. They glow or darken. They invite rain or delay it. They nurture life through nutrient delivery. They soften the sun's blaze into a warm disk on hazy afternoons. Again and again, the quiet repeats increase our confidence that these processes matter for the climate story. None of this is rushed. Research accumulates. The mind can rest in that. To make this more personal, return to the simple image of a sunbeam crossing a quiet room. Dust dances in it, slow and patient, turning and gliding, rising and falling with currents too faint to feel. Each mote is lifted by the same physical laws that carry aerosols across continents. If you pause and watch long enough, you might notice patterns that repeat in the air movement. It is soothing to watch, a moving meditation that mirrors the planet's own movements. Now, imagine that beam scaling up to a shaft of sunlight through a break in marine stratocumulus, and the particles expand in number to fill a column of air from ocean to space. The analogy holds. The gentle rhythm continues. We can follow one aerosol on a whimsical path. It begins in pine forest air, formed from the slow reaction of a terpene. It grows enough to become a seed that would take water if the air offered it. A cumulus cloud passes overhead and lifts the air a little. The particle activates, becoming a tiny droplet that sparkles in the cloud edge. For a few minutes, it resides in that bright wall where sunlight refracts into glories and coronas. Then a mixing eddy brings drier air into the cloud, and the droplet evaporates, leaving the particle slightly larger than before. It rides out of the cloud and descends. Hours later, it meets the plume from a passing vehicle, gains a coat of organic material, and floats on. Near sunset, humidity climbs, and it takes up by water again, even without becoming a cloud droplet. It grows and scatters more light. The sunset looks softer by a shade because of it. A breeze carries it toward a lake. Overnight, a thin fog forms and wraps it in water again, and this time the droplet settles onto a reed as dew. In the morning, the sun warms the dew and the water evaporates, perhaps leaving the particle behind on the reed, or perhaps resuspending it to continue. The gentle rhythm continues, a cycle of forming and dissolving that could repeat many times. Consider also a sea salt particle as it crosses from open ocean into a busy harbor. In the open air, it is one among multitudes, meeting no obstacle, growing and shrinking with humidity. Near the harbor, exhaust fumes and urban plumes coat it. It becomes less pure, perhaps a little less eager for water, but still ready to seed a droplet when the marine layer swells overnight. It lands on a building, and the next gentle rain rinses it into a small gutter that leads to a larger drain and then to the sea. In this way, the particle returns home. The path is quiet and complete. Dust has its own personality. It is irregular, like a tiny shard of a mosaic. It does not love water, but if coated with a bit of nitrate or sulfate in the air, it can soften and become more accretive. Its role in ice clouds is special. Certain mineral faces encourage ice to form at warmer temperatures than it would otherwise. In a high cloud of ice crystals, a small number of such particles can set the stage for the cloud's appearance. Picture a cirrus sheet at dawn, a high, delicate veil. Those who study these clouds take care to understand which aerosols most effectively nudge water toward ice, because the radiation budget at night and during the day depends on these subtle shifts. Again, the outcome is slow and cumulative, not theatrical in any moment. A quiet chapter in the aerosol story lies in the southern hemisphere's high latitudes, where the air is often cleaner and the sky and sea are in a slow waltz. There, The natural cycle of biogenic aerosol formation, sea salt production, and cloud brightening can be seen with fewer interruptions. Haze lines on the horizon are finer. The marine layer spreads broadly. Residual layers sit softly above, revealed only by the way they slightly dim a setting sun. The gentle rhythm continues, a planet's edge breathing in long, smooth waves. Back toward continents, layers of aerosols can form in steps with height, like terraces. A morning layer near the ground, a transported layer above, and a residual layer from the day before. Each has its own story. The ground layer holds the freshest mix from surface sources. The transported layer is the atmosphere's memory of a region hundreds or thousands of kilometers away. The residual layer is yesterday's breath, lifted by air heating and trapped aloft by the evening's cooling. Instruments trace these layers, and on some days, these recordings are like a soft barcode for the skin eye, each line a slightly different shade of gray. To end these observations gently, it is soothing to acknowledge the balance between the measured and the felt. The measured tells us that aerosols are numerous, varied, and influential in a climate sense, with effects both direct and indirect. The felt tells us that the air has texture, that light changes in subtle ways we notice without naming, that clouds have seasons and accents. These two ways of knowing meet in a quiet recognition that small things matter, and that they matter most when many of them act together, as they always do in the air above us. As your eyelids grow heavier, bring to mind once more the image of tiny particles on a languid voyage. They drift through sunlight and dormancy, through moisture and dry air, through formation and removal while we carry on with life below. They travel the way you drift toward sleep, slowly and inevitably, guided by a larger rhythm. Imagine yourself floating alongside one, seeing the world in miniature, listening as the wind changes key from day to night, watching clouds form like breath on glass. Each moment is simple, each moment is soft, and together they steer big climates, not with abrupt turns, but with a continuous, tender pressure that is always present. If you're still listening, know that you are safe and at ease. The room is quiet, the night is kind, and the world will continue its gentle patterns without asking anything more of you. Let the concepts settle like fine mist, and let your thoughts move apart like clouds after rain, revealing a calm blue beneath. Thank you for spending this slow time with me. If this helped you relax, a like and a subscribe help us keep making these soft journeys for you. And the playlist is waiting whenever you want to learn without urgency as you drift. Rest well, breathe steadily, and let sleep arrive on its own gentle timetable.